Welcome back to all. So in this lecture I will talk about the theory that is called Virial Theorem. So basically this Virial theorem relates the expectation values of kinetic energy and potential energy of atoms and molecules. So basically I just recollect whatever we have understood about the structure of hydrogen atom. So you know that this is a three-dimensional coordinates, as you can see. So you can see that these are three-dimensional coordinates where the center is called the nucleus, and around which and the electron is basically residing at some point that is called this point, and the distance between the electron and the nucleus is called the r, and you can see this is the mass of the electron me, and this is the mass of proton. So this is the structure of the or quantum mechanical structure of hydrogen atom, where the electron can reside any one of the three-dimensional space around the nucleus. So we have derived previously that the expression value for energy for hydrogen atom is basically equal to minus me e to the power 4 by 32 pi square epsilon 0 square h cross square 1 by n square. So this is the energy expression for hydrogen atom for any principal quantum number n. So this n is basically the principal quantum number, so n can have any value in between 1, 2, 3 to infinite. Okay, so me is basically the mass of the electron, and epsilon 0 is basically the permittivity of the space in between the nucleus and the electron. So you can see that energy is inversely proportional to the square of the principal quantum number. Now another thing, that it is always good to express the position of the electron in terms of the polar coordinate, as the potential energy is dependent upon this r. Okay, so there is another factor r. So basically energy is not depending upon the r, that is the distance between the nucleus and the electron, but as you know that the total energy is equal to the potential energy and kinetic energy. Kinetic energy is sometimes often expressed as T. Now this potential energy, as it depends upon the distance between the nucleus and the electron, so that's why it is always better to describe the position of the electron in terms of the polar coordinate. So in polar coordinate, what we will do in 3 dimension, so you can see this is the 3 dimension. So in polar coordinate, suppose this is the position of the electron. So we describe the position of the electron by 3 value theta, phi, and it is r. So the position basically or the wave function of the electron is basically described in terms of the r, theta and phi. So this representation is called the polar coordinate representation. Now you can know that there are the operator, that is the Hamiltonian operator. So this Hamiltonian operator is basically associated with the total energy of the system or the electron. So this Hamiltonian operator is basically consists of 2 operators, that is kinetic energy operator and potential energy operator. Now the kinetic energy operator that for hydrogen atom we have discussed previously is equal to minus h cross square by 2 me into delta square, but this delta square is basically nothing but Laplacian operator. So this delta square is basically del by del x square plus del by second derivative with respect to y square second derivative with respect to z square. So this is basically in Cartesian coordinate. So if you want to express the kinetic energy in terms of the polar coordinate, you have to you can convert it, but and those conversion and those process were already described in the hydrogen atom portion. So this is the expression of the kinetic energy. Now here it is important that sometimes in most of the cases we have described this mass in terms of the reduced mass mu e. So the reduced mass mu e is basically me in mass of the electron plus mass of the proton by mass of electron plus mass of proton. But as in this case the mass of the proton is much higher than the mass of the electron, so that's why the mu e became almost equal to the mass of the electron. So that's why we will use the mass of the electron to describe the kinetic energy operator. Okay, so this is basically the approximation, that instead of using the reduced mass we will use the mass of the electron. Now coming back to the potential energy operator. Now as you can see, the potential energy operator is basically Q1 into Q2 by so there is a one minus sign, Q1 into Q2. So the charge of both electron and nucleus is E and E for hydrogen atom into 4 pi epsilon 0 into R. So you can see that this potential in case of this potential energy operator, there is this term R. So R is basically the distance between the nucleus and the electron. So as you can see that this potential energy term is present in the so this R term is present in the potential energy operator. So it is always better to express the position of the electron in terms of the polar coordinates. Okay. Now coming back to the ground state of atomic orbital for a hydrogen atom. So we have derived that the expression of the ground state wave function, that is psi 110 for hydrogen atom, is equal to root over of pi z by a0 3 by 2 e to the power minus zr by a0, where you can see that for hydrogen atom z is basically number of proton, that is equal to +1, and a0 is called the Bohr radius, which has the value of 52.9 picometer. Okay, so this is called the Bohr radius. Now you can see in that expression of the wave function for the ground state, you can see that the psi is basically a function of n, l, m. So that n is equal to 1, this l, that is that orbital angular quantum number, this is equal to 0, and this m is basically the magnetic quantum number, this is equal to 0. So this is the ground state wave function, or for wave function of 1s orbital. Okay. Now the expectation we have learned in our quantum mechanical chapter, that the expectation value of a property in a spherical polar coordinate can be expressed like this. So suppose this a is basically any property, expectation value of any property. So the expectation value can be obtained by this equation, integration 0 to 2 pi d phi pi sin theta d phi, sorry d theta, into integration 0 to infinite r square dr psi star nlm, the a operator associated with this property, into psi nlm. So this is the expression to determine the expectation value of any property. So you can see here we will compute the expectation value of the potential energy and kinetic energy of hydrogen atom model in 1s state. Okay, so the 1s state means psi 100. Now as you know, the expression for the potential energy of operator will be equal to minus E square by 4 pi epsilon 0 into R. So the expectation value for potential energy for 1s orbital or the ground state of the orbital will be equal to 0 to 2 pi d phi integration 0 to pi sin theta d theta integration 0 to pi. Here you can see that the wave function for hydrogen psi 110, that is 1s orbital, is equal to 1 by root over of pi by z by a0 3 by 2 into e to the power minus zr by a0. Now you can see that there are these are all real number. So if you write the value of that is r square into psi star 100, so the psi star 100 will be same as this one because there is no complex number present. So you have to take the psi square value. So the value of psi square is equal to 1 by pi a0 cube into E square. So this is the potential energy operator that you will insert there, epsilon 0 r into r square e to the power minus 2r by a0 dr. Okay, so this is the expression for the potential energy. Okay, now you can see that you have taken the square of this value. Z is basically equal to 1, so if you take the square of this value you will obtain 1 by pi a0 cube, and again if you take the square of this value you will obtain this one, e to the power minus 2r by a0, and r square is always there because and the operator that is operating in between is this one, and there is one negative sign. This is the potential energy operator that is operating. Now this value is basically equal to 2 pi. That is very straightforward, and you can see what is the integration of 0 to pi sin theta d theta is equal to 2. You can easily determine it. Now we have to concentrate on this integration. Okay, so you can see this 2 pi and this 2 pi into 2 will be equal to 4 pi. So this 4 pi by 1 by pi a0 cube, this term are not depending on r, so this term will be out of the integration. So the term that will be outside of this integration will be equal to 4 pi by pi a0 cube, that is into, so there is another constant term that is minus e square by 4 pi epsilon 0. And there is the integration 0 to infinite r. So this r and this r will cancel out, so there will be only one r that will be remaining. So sorry, this r, there is only one r, this r will not be there, so this r and this r will cancel out, so only one r will be remaining there, so that this integration will be r into e to the power minus 2r by a0 into dr. Okay, so we have to solve for this integration. Now the solution of this integration can be obtained from the integration table. So if you go to the integration table, you will obtain one formula, that is integration 0 to infinite x to the power n into e to the power minus ax dx, that is equal to n factorial a into n plus 1. So if you see the similarity between this equation and this equation, you can see that in this case the x is basically replaced by r. okay, and so the variable is r instead of x. So if you just compare these two integral, you will see that n is basically equal to 1 and a is basically equal to 2 by a0. Okay, so by comparing this, so this is the solution. So the solution of the integral will be equal to n is equal to 1, so 1 factorial will be equal to 1 by a is 2 by a0 into n plus 1, it means 1 plus 1. So the solution of this will be a0 squared by 4. So this is the solution of this integral. Okay, now what is the expectation value for potential energy for 1s state? That will be equal to 4 pi into pi a0 cube into 1 minus term will be there, e squared by 4 pi epsilon 0 into this a0 squared by 4. So you can see that this 4 and this 4 pi and this 4 pi will cancel out. Okay, and this a0 square and this a0 will cancel out to give 1 a0. Okay, so the final expression that you will obtain is basically minus e square by 4 pi epsilon 0 a0. So this is the expectation value of the potential energy. So this tells us that the average value of the radius from the perspective of the potential energy is the Bohr radius a0. So, and you can see that the average distance, so the average distance from the perspective of the potential energy is nothing but a0. Okay, so you can also determine that a0 is basically and now we will determine if you can actually replace this a0 value. So previously I will go to the so as you can see that the potential energy V1 is the average potential energy is equal to minus e square by 4 pi epsilon 0 a0 that we have solved right now. Now the expression of a0 that is the expression of Bohr radius that previously we have determined is equal to epsilon h cross square by pi me e square. So if you just put this value here, you will obtain the potential energy expression is equal to minus me e to the power 4 by 16 pi square epsilon 0 square h cross square. So this is the average potential energy for 1s orbital. Now if you see closely that for hydrogen atom the energy of the 1s orbital is basically equal to minus me e to the power 4 by 32 pi square epsilon 0 square h square. So if you just compare this, you will see that the potential energy is almost double than the total energy of the hydrogen atom. Okay, so this is the total energy for the hydrogen atom and this is the potential energy of the hydrogen atom. So you can see that the V, that is the potential energy of 1s orbital, is basically 2 times than the expectation value or the average energy of the hydrogen atom. Now we have known that the expectation energy of hydrogen atom 1s orbital is basically sum of potential energy of 1s plus expectation of kinetic energy of the 1s. So if you just put this, So there is one 2 term will be there, 2 plus 2 into kinetic energy of 1s, which is equal to, so if you just take out this potential energy to right side, or you can take the average potential energy of 1s will be equal to minus 2 average kinetic energy of 1s. So if you just take the ratio of the average potential energy of 1s by the ratio of average kinetic energy of 1s, you will obtain minus 2. Okay, so the final Virial theorem, that is you can see that the Virial theorem, that the main concept of the Virial theorem that we will discuss here, the main outcome of this Virial theorem, we can say that that we have derived that the potential energy of 1s, the ratio of the average potential energy of 1s orbital and average kinetic energy of 1s orbital is equal to minus 2. But the actual Virial theorem is very broad, so it is not only this is what Virial theorem says, but this is not only applicable for 1s orbital. So this normally true for 1s orbital for hydrogen, but it is also true for all the atomic orbital, for all atomic orbitals of hydrogen, all atomic orbitals for hydrogen like atom like helium plus lithium 2 plus, or it is also true for all atoms that have multiple number of electrons, and it is also true for molecules with multiple nuclei. So it is true for anything where the potential energy is just a Coulombic potential term, so generated by the bunch of nuclei. So this equation, that is the average of the potential energy and the average of the kinetic energy, that is equal to minus 2, is applicable for any atom or any molecule in which the potential energies basically arises due to the Coulombic interaction between the nucleus and the bunch of the electron that is present. So if the potential energy contain only the Coulombic interaction term, then this general theory, that is called the Virial theory, will be applicable, but the ratio of the expectation value of the potential energy and kinetic energy will be equal to minus 2. So this Virial theorem is very broad, and you can actually use this Virial theorem as a metric when we have a approximate wave function. So sometimes our wave function is not exact wave function, sometimes we have to deal with approximate wave function that I will discuss in my other lecture. So sometimes when you are actually working with some approximate wave function, so in that case you how to determine whether our wave function is very good approximation of the actual function or not. So by seeing that how much this Virial theorem is being applied for this system, from that we can actually say that how much our this approximated wave function is close to the actual wave function. So if it is very close to this Virial theorem, if it is following this Virial theorem very closely, if we use this approximate wave function, then we can say that our approximate wave function is basically very close to the actual wave function. So you can see that this Virial theorem is can be used as a metric when we are having some approximate wave function, and how good they are depending upon how closely this criteria of Virial theorem is being matched. So that is up to this for this lecture. If you have any question regarding this lecture, you can ask me through the comment section, and please subscribe to my channel Chembiosis for more update or for more lecture like this. And in the next lecture I will discuss about the Zeeman effect. So till then take care of yourself. Bye.